Okay, now, in some ways, I was just mentioning this to him, in some ways, this practice test does not complete enough. I'm gonna be adding some reaction testing. So make sure that you add these reactions to your practice test. You can also have a 3x5 card both sides. One 3x5 card. Done 3x5 card. Okay. Name these guys. All right, well, first of all, it's a ketone. So it's gonna have an ONE at the end, and it's a six-sided. We have two branches at so 2,3-dimethyl cyclohexanone. Okay, so that was a ketone, which is an aldehyde. So it's 1, 2, 3, 4, 5. It's a pentanal. Got a branch at carbon number 2. 2-methyl pentanal. Really. 3 parts. Draw these structures. Okay. It's a ketone. 7 carbons long, carbon number 3. So 1, 2, 3, 4, 5, 6, 7. 1, 2, 3. We've got on carbon number 2 a phenyl branch. And a number 6, a bromo branch. Okay. Butanol. A 4-carbon alcohol. Alcohols in carbon number 1. And here we have 2 methyl groups. Carbon number 2. Pentanal, 5-carbon aldehyde. Carbon number 2 is isopropanol. And then 3, 4 are 2 methyl groups. Okay. Beta galactose. Anomeric carbon. Alpha fructose. Okay. So we have a di. We have a disaccharide, and it's got two glucose molecules, so it's going to be maltose. And it's going to be alpha maltose because of the anomeric carbon on the right. Is it a reducing sugar? Yes. Why? Because it has a hemiacetal here. Well, let's do this differently here. Name a test you would use to determine this. Okay, there are two tests. One would be Benedict's. And let's just draw the reaction for that. Okay, so we're going to start with maltose. Okay, so you start with the closed ring. And this was alpha malt. Yeah. Okay. So the next step is opening the ring up. And this is going to be in a alkaline or basic environment. Okay, so now the ring is open, exposing the aldehyde. So we're going to add the Benedict solution, which is copper. So what's going to happen is that copper is going to be reduced and oxidize the aldehyde to the corresponding alcohol salt. I say salt because we're in an alkaline environment. Okay, so what does that look like? So the glucose on the left is going to be unchanged. Okay, so we have copper's being reduced. The aldehyde is being oxidized. Now that's going to be your trickiest reaction. So it doesn't matter what we put in here as a monosaccharide, disaccharide, oligosaccharide. Still going to have the same reaction, oxidation and reduction. Named linkage, okay? So if we look at the linkage, okay, here's the anomeric carbon. So this is carbon number 4, carbon number 1, so it's going to be a alpha 1 for glycosidic linkage. Okay, there any questions about this guy? So you should be able to substitute in fructose, galactose, glucose, maltose, lactose, sucrose into that. Now, sucrose is not going to be reducing sugar because there's no hemiacetal. So it'd be no reaction. So we go blue to blue. All the others, there's a hemiacetal present, which means it'll go from blue to orange. Kind of an ugly, rusty color. Yeah.
Over the acidity.
Okay, so whenever you have di-oligo or polysaccharide, you have a linkage. Okay, that's connecting the monosaccharides together. And it's two parts on the linkage. So on the left here, carbon number 1 at the anomeric carbon, it can be either alpha or beta, up or down. That's what that signifies, is it's going down. And what is it connecting to? Carbon number 4. Now, carbon number 4 has to go down. Otherwise, it wouldn't be glucose. So sometimes, like when you look at sucrose, sucrose has got one anomeric carbon connected to another anomeric carbon. Now, as soon as we connect to an anomeric carbon, it can be up or down. So you have to say alpha or beta. So let me do sucrose for you. Okay, and sucrose is kind of a vertical molecule. So it's going to be so we've got glucose on the top, and it's going down to connect to the fructose. So as soon as it goes down, that's an alpha 1 going down because it's alpha. And what is it connecting to? Well, it's connecting to fructose here. And this OH is going up, so that's a beta. And that's carbon 1, 2, so it's beta 2. So it's an alpha 1, beta 2. See where the alpha and betas come in?
You see that?
Yeah, because fructose by itself looks like this. Now, let me finish this here. Okay, so that's sucrose. Okay, and this is the anomeric carbon. So on fructose, anomeric carbon is carbon number 2. One. Okay, so if we look at fructose by itself, so this here can be up or down, depending whether it's alpha or beta. Now, in this case, it's beta because the OH group is going up. And again, it has to do with the anomeric carbon. It's the only one where it matters, is anomeric carbons. So this is going up. That's why it's a alpha 1 beta 2. Is that better?
Yeah. I think it's-
So this is sucrose, fructose, and this is beta fructose. Okay, so what disaccharide has an alpha 1 beta 2? Sucrose. Oops, wait a minute. What is meant by the term reducing sugar? Okay, reducing sugar has a hemiacetal presence. Opens to an aldehyde, and number 2, it can be oxidized. Okay, I'm not going to draw the structure again because it's right here. Now, some books show it incorrectly. They don't have the anomeric carbon on the right. They have it on the left. Biology books particularly have it that way. But you have to connect anomeric carbon to anomeric carbon, and by standard, anomeric carbon's on the right. So is it a reducing sugar? Okay, so let's analyze this. We have OCO and OCO. It's 2 of them. Top one is OCO, and we have we have no H's. Excuse me, we do have an H right here. We have no OHs though. So that means that is an acetal. Because the H is present. Okay, let's look at this one down here. And we have an H present. No. And no OH. So this is a ketal down here. So the reason why it's not a reducing sugar, it doesn't have a hemiacetal present. Okay, blue indicates it's got a embedded monosaccharide in it. Which one is it? Well, we look at this guy here. This is glucose. Okay. And with the OH going up here, it's going to be a beta glucose. Okay, is it reducing sugar? No. No hemiacetal. Okay, circle the area in question. That area. So we have OCO, H, no OH. Hence that is an acetal. Okay, polysaccharides. Polysaccharides. There were three, actually four. You had amylose, which is considered starch. We had amylpectin, which is a branched starch. Then we had glycogen. Okay, glycogen is the only carb made in mammalian systems. Amylose is straight with an alpha 1,4 linkage. Amylpectin has two linkages. There's an alpha 1,4 and an alpha 1,6. Glycogen has got alpha 1,4, alpha 1,6. Glycogen tends to be more branched than amylpectin. Amylpectin is vegetable based, glycogen is mammalian based. Okay, I've already done this reaction up here with maltose. So the difference between the two is the glucose on the left wouldn't be there. First step, the ring opens up. To an aldehyde, I'm going to throw in copper nitrate, which is a +2 charge. And it's going to be in a alkaline or basic environment. So the glucose becomes oxidized now. To the acid salt. Copper goes from +2 to +1. That's the part that's being reduced. And then the aldehyde is being oxidized to the acid. And because it's a basic environment, it's oxidized to the acid salt. Now, so what's missing in this are reactions. No reactions in this OPA of a test. You know, after I passed this test out last semester, I'm like, crap, there's no reaction, but I already passed it out. Okay, but so normally this is the harder of the 4 tests. So let's practice some reactions here. We've already gone through the reactions of carbs. There's the Benedict's, mostly the Benedict's reaction. But let's look at aldehyde ketone reactions now. All right, let's make that. Okay, so we have OCO. So let's analyze this before we go anywhere, okay? OCO, H, no, OH, yes. So that means this is a hemiketal. Okay, so we have a primary and secondary backbone. Primary is a 3-carbon ketone, anomeric carbon here. So that means we need to start with a 3-carbon ketone because it's a ketal. We need to add in an alcohol now with a secondary backbone is there. Okay, which is a 2-carbon ethanol. So with these type of reactions, acetals and ketals, you don't have to name it. You just have to say what it is, doing the OCO tests. So this is a hemiketal, and we have ethanol here. And we have 3-propanone. Okay, typical aldehyde ketone reaction. Yeah.
How is it a hemiketal if there's no hydrogen?
You can only have an acetal if there's a hydrogen present. There's none. So that means it automatically becomes a ketal.
So OH is the hemi, would be the, so if
Yeah,
it was,
the OH is the hemi part.
okay, got it. Okay, I had that mixed up. Thank you.
Okay, so let's take 3-propanone again. And let's oxidize it. What's our product? Now remember, you're gonna have a flow chart. You don't have to memorize that. What is the product gonna be? Can ketones be oxidized? No, so no reaction. Okay. Some people go, oh, that was a trick question. It was an easy question. Don't have to write out any products there. Okay, so let's try some more here. Let's take this guy. And oxidize it. Okay, so this isn't ketone up here. This is an aldehyde. So what do aldehydes do when they're oxidized? Comes an acid, right? Now notice I have the OH on the acid. That's because it's in either neutral or acidic environment. If it's alkaline, we have the acid salt then. We have O minus. Okay, so let's look at this guy here. Okay, we got 1, 2, 3, 4. 1, 2, 3. Yeah, okay. And let's see, we have, this goes to the acid. You don't have to name acids because that's unit 3, which I've done 2 lectures now in unit 3 already. I did those last week for videos. Okay, so what do we got here? Okay, so we've got a 1, 2, 3, 4 carbon aldehyde. So that's going to be a butanal with a methyl group on carbon number 3. So that's 3 methyl butanal. And this is going to go, I'm just going to name this. Now, unit test 3, you're going to have to name these acids. Okay, so that's a 3-methyl butanoic acid. Now, if I put 1 ethanol there, that means the reaction is going to go once. If I put 2 ethanols, that means it's going to go twice. So let's first do it with just 1. Okay, so we have a ketone and an alcohol. That means we're going to form a ketal. So this is 1, 2, 3, 4. So that's 2 butanone. And this is ethanol. And let's make it an acidic environment. Okay, so now we have primary backbone, secondary backbone. So let's do the primary backbone, and this will be the anomeric carbon here. And then here, because it goes only once, it's going to be the hemi version. So it's going to be a hemi ketel. Now let's do throwing in another ethanol. So if we take this now for the second alcohol, bless you. Oh yeah, and then throw in my hay fever from last week too, on top of all that crap I was going through. Okay, so now we're going to add another ethanol. So we have a so we have OCO, no H, and no OH. And that means that is a ketel. Hey, you guys, you doing okay? For the first reaction? Okay, well, aldehydes and alcohols connect up. They connect up at the carbonyl on either the aldehyde or the ketone. The first time it becomes a hemi, and then the second time it attaches the same spot again, but it becomes a full-blown acetal or ketel. So was that kind of your question?
I. I'm not going to get lost.
Okay, so we're going to add the secondary backbone with an O. And that just attaches where the carbonyl was. with an with an OH the first time through. The next time it attaches in the same spot, but no OH. So you've got an O secondary backbone and O again secondary backbone. It just all focuses on the anomeric carbon. That's why I was put a dot by it. Textbooks and stuff don't put dots there. Only I put dots there. Oh, let me, one more thing here. Okay, so let's do some more reactions here. Okay, so that's a ketone. What happens when you reduce a ketone? Exactly. Perfect. Secondary alcohol. So this is going to be cyclohexanone. And this is going to be cyclohexane. hexanol. And then throw in any branches or whatever. Okay, two different ways to make this. Okay, it's a 1, 2, 3, 4. So it's a one butene. So how can we make that? Well, we make from an alcohol. We can pull off water from an alcohol, and we'll end up with an alkene. Okay, at high temperature. Okay, so we're gonna have the same backbone. So this would be a 1-butanol. And then we have you can pull off water, but it's a high temperature. Okay, what's another way? This way is trickier. Second way. What do you think? What will the aldehyde give us?
Go from an aldehyde to alcohol.
And then alcohol to
Alkene.
perfect. All right, this is what she said. Instead of starting with an alcohol, let's start with an aldehyde, and we have an aldehyde, we can get an alcohol. Okay, so we're going to reduce the aldehyde, which goes to an alcohol. And then we're going to do the same reaction above. Oops. Okay, so we have butanol being reduced to butanol. Going to butene. So that's a multi-stepper. We're gonna have very few multi-step problems in here. Usually I have one per test. All the rest will be single shots. Now, since we're not gonna have a final, I always have questions from the past unit. Well, the past unit's unit 1. So let's do some unit 1 reactions. Well, we just did one right here. That's a unit 1 reaction. How about if we did the same reaction under different conditions? What will we get then? Hmm? Ether, yes. Yeah, under less strict conditions, the alcohols are going to link up together. So to do that, then I'm going to flip it horizontally. So this is going to be a so this is going to be dibutyl ether. Oh, let's see. I'm trying to visualize a flow chart here. Would be a good reaction. Okay, so we're going to throw water across that double bond. So this is 1, 2, 3, 4, 5, 6. So it's going to be hexene. 1, 2, 3, 3 hexene. What are we going to get? One alcohol, two alcohols. Actually, we're going to get, if you flip them, they'll be the same. Let's do this a little differently. Let's do that instead. So we're going to get a mix. If you notice on your flow chart, you'll see expect mix. So that means we're going to have OH here and OH here. Those would be the two alcohols we generate because the OH is going to be either side of the double bond. Remember, water looks like this. So it's heterogeneic, generic. So it can be either H, OH, or OHH. Okay, then we need to name these. So it's going to be Which is more stable, red or blue? Hmm? Which one? Red, why? What?
Symmetry.
Okay, symmetry, yes, it's very balanced. That's why I threw in the extra carbon, so we get two different molecules. So symmetry for sure. The red is nice and symmetrical. It's got the OH in the exact middle. Where the blue is lopsided. So symmetry wins. Now Markovnikov, okay, let's count terminal hydrogens. Okay, we've got 3 here, 3 here. 3 here, 3 here. So Markovnikov, it's a wash. You can't tell from Markovnikov. The only one that wins is symmetry. So let's see. Is everyone okay with that? Number one, the two products you get, plus which one is more stable? Symmetry wins. Okay. Well, I can't think of any more examples here. Okay, so those are some examples, reaction examples. Just go through your Unit 2 dry lab worksheets. Okay, so what I'm going to do now is